The cleanest particle collision signature in physics is showing a pattern that will not flatten out. And the reason it matters is that clean channels are where real anomalies hide best. When four leptons emerge from a proton collision, every part of the event can be tracked, measured, and reconstructed with almost no ambiguity. There is no missing energy, no invisible neutrinos escaping, and no chaotic background from the strong nuclear force drowning the signal. That is exactly why physicists use this channel to test whether the Higgs boson behaves the way the standard model predicts. But what happens when the cleanest filter in particle physics keeps showing the same subtle irregularity, even as more data pours in and better models are applied? The question this episode answers is how a faint pattern in four-lepton data became impossible to dismiss as routine noise, and what that means for the foundation of the standard model. The first clue is simple. Precision itself has become an accusation. When the data is clean enough to resolve mass peaks with better than 2% accuracy, any persistent mismatch stops looking like a mistake and starts looking like a message. Before we walk through what makes this pattern dangerous, here is one immediate reality check. If the anomaly were just a software ghost or a detector flaw, it should wash away when you add more collisions or refine your background models. Instead, the residual is becoming sharper. That tells you the problem is not going away by itself. The Higgs boson decays into two Z bosons, and those Z bosons then decay into four leptons. Leptons are electrons and muons, particles that leave clean, bright tracks in the detector. Unlike quarks, which spray out messy jets of hadrons, leptons are simple. You can measure their energy, their direction, and their charge with extreme precision. That is why this decay channel is called the golden channel. It was one of the key pathways used to discover the Higgs in 2012, and it remains the most reliable way to measure the Higgs mass and check its properties. The process is straightforward. A Higgs boson is created in a proton collision, exists for a fraction of a second, and then decays. One of the two Z bosons is usually virtual, meaning it is off-shell, existing only as a quantum fluctuation that borrows energy from the vacuum and pays it back almost instantly. The four leptons that emerge carry the full story of what happened. You can add up their energies and momenta to reconstruct the original Higgs mass. You can measure the angles between them to test whether the Higgs has the right quantum spin. You can compare how often electrons appear versus muons to check a principle called lepton flavor universality, which says these two particles should behave identically in this context. The standard model makes very specific predictions about all of this. It tells you what the mass spectrum should look like, how the leptons should be distributed in angle and energy, and how the signal should separate from background events, like ordinary Z boson pairs produced without a Higgs. The tension begins when you look at the high-energy tail of the four-lepton mass distribution. This is the region where the combined mass of the four leptons is much higher than the Higgs mass itself. In this regime, the events are rare, the statistics are thin, and the data becomes extremely sensitive to how you model the background. The standard model predicts a smooth falling curve. What experimentalists are seeing instead are structured residuals. These are not random fluctuations scattered above and below the expected line. They are geometric patterns, persistent bumps and dips that stay in the same place across multiple analyses. When you increase the number of collisions, these features do not dissolve. When you update your background, models with better Monte Carlo simulations, the residuals shift slightly, but do not disappear. When you compare data from ATLAS and CMS, the two independent detectors at CERN, hints of similar shapes appear in both, though not with identical strength or location. That combination is what makes the pattern hard to dismiss. It is not dramatic enough to claim a discovery, but it is too stubborn to ignore as a statistical accident. One possible explanation is that this is a background modeling error. Calculating how ordinary Z-boson pairs behave at high energies is difficult. The process involves quantum interference between multiple diagrams, and small mistakes in how you simulate those diagrams can create fake structures in the data. Another possibility is that the anomaly comes from how physicists classify events. When you divide a continuous mass spectrum into bins, the width and position of those bins can accidentally hide or exaggerate faint signals. If you choose narrow bins, you get better resolution, but worse statistics. If you choose wide bins, you smooth out real features. This is not a trivial choice. It is a high-stakes decision that can make the difference between seeing a hint and seeing nothing. A third possibility is more interesting. The residuals might be real, caused by a new particle or interaction that the standard model does not include. If a heavier, unknown particle exists and can decay into the same four-lepton final state, it would interfere with the Higgs signal through quantum mechanics. That interference would distort the shape of the mass spectrum in exactly the kind of subtle, energy-dependent way that is being observed. The problem is that you cannot tell which explanation is correct without more data, better simulations, and independent cross-checks. What makes this channel especially sensitive is completeness. In most particle decays, something escapes. Neutrinos carry away energy you cannot see. Quarks turn into jets that spray particles in all directions, making it hard to trace everything back to the original event. But in four-lepton decays, every piece of the puzzle is visible. You can reconstruct the full kinematics. You can measure every angle, every energy, every invariant mass. That completeness is a gift for precision, but it also means there is no place for errors to hide. If your detector mismeasures even one lepton, it can pull the entire event into a suspicious region of the mass spectrum. A single bad track can sculpt a fake tail in the distribution, mimicking the signature of new physics. That is why physicists use a technique called blinding. They freeze their analysis cuts and selection criteria before they look at the data in the signal region. This prevents unconscious bias from tuning the analysis to create a discovery that is not really there. When the analysis is unblinded and the residuals are still present, that is when the pattern becomes a target. The standard model also predicts lepton flavor universality in this channel. Electrons and muons are identical except for their mass, so the Higgs should produce them at the same rate, and they should behave the same way in the detector. But the data is showing faint differences. Events with muons are not quite matching events with electrons in certain kinematic regions. The difference is small, only a few %, but it is persistent. If confirmed, this would be a direct violation of a core symmetry in the standard model. It would mean that something is treating electrons and muons differently, and the only way that can happen is if there is a new force or particle coupling to mass in a way the current theory does not account for. This is not an isolated tension. Similar muon-related anomalies have appeared in other experiments. At Fermilab, the muon magnetic moment measurement disagrees with the standard model prediction by more than 4 standard deviations. In B meson decays at LHCb, certain processes involving muons happen less often than they should. These anomalies do not prove anything by themselves, but they rhyme. They suggest that the muon might be a window into physics beyond the standard model. Another connection comes from B meson flavor anomalies. These are deviations in how B mesons decay into lighter particles, particularly in channels involving leptons. The mathematical structure of these anomalies shares features with the four-lepton tension. Both involve flavor-changing processes, both show electron-muon asymmetries, and both appear in precision channels where the standard model makes very specific predictions. If both anomalies are real and connected, they could point to a new force or particle that couples preferentially to second and third generation fermions. This would explain why muons behave differently from electrons, and why certain rare decays are suppressed or enhanced. But the connection is speculative. The anomalies could also be unrelated, each caused by different systematic effects or statistical flukes. The only way to know is to keep measuring. The danger of the high-mass tail is that it is a low statistics region. When you have only a few dozen events in a bin, even small uncertainties in the background model can create large residuals. Systematic uncertainties start to dominate. You have to account for how well you know the detector efficiency, the trigger acceptance, the lepton energy scale, the pileup from multiple simultaneous collisions, and the theoretical uncertainties in the signal and background cross-sections. All of these uncertainties add up, and at some point, you hit a wall. You cannot tell if the data is wrong or if the theory is incomplete. That wall is where physicists are now. They have pushed the systematic uncertainties down as far as current methods allow, and the residuals are still there. The next step is more luminosity, more collisions, more data. If the pattern grows stronger as the sample size increases, it becomes a discovery. If it fades, it was noise. One forensic detail matters here. When analysts compare ATLAS and CMS results, they are not looking for identical signals. The two detectors have different geometries, different trigger systems, different reconstruction algorithms, and different systematic uncertainties. A real new physics signal should appear in both experiments, but it might look slightly different in each. What matters is whether the residuals in both datasets point in the same direction. If ATLAS sees an excess at a certain mass and CMS sees a deficit, that is a red flag. If both see an excess, even if the statistical significance is different, that is a green light. So far, the comparison is ambiguous. Both experiments see hints, but the hints are not strong enough to claim consistency. That ambiguity is frustrating, but it is also honest. It reflects the true state of the evidence. The survivor principle is simple. When you apply new data, better models, refined cuts, and independent cross-checks, most anomalies disappear. They turn out to be statistical flukes, detector artifacts, or modeling errors. But some residuals survive. They stay on the screen. They shift slightly when you change the analysis, but they do not vanish. Those are the residuals that become physics targets. The Four-Lepton pattern is a survivor. It has been present in multiple datasets, multiple analyses, and multiple energy regimes. It has survived upgrades to the background models, refinements to the event selection, and comparisons between ATLAS and CMS. It is not strong enough to be called a discovery, but it is too persistent to be called noise. That is the definition of a precision threat. It is boring, it is subtle, and it is exactly the kind of signal that could rewrite the standard model without anyone noticing, until the evidence becomes overwhelming. So, here's the answer to the title question. The Four-Lepton channel has eliminated the possibility that this residual is a random statistical fluctuation or a simple detector error. The pattern has survived too many tests and too much new data for that. What the evidence cannot yet explain is whether the residual comes from an incomplete background model, a subtle bias in how events are classified, or a genuine new particle interfering with the Higgs at high energies. The mechanism remains open because the statistical significance is not strong enough to rule out any of these possibilities. What is no longer open is the idea that this is routine cleanup. The cleanest channel in particle physics is accusing the standard model of being incomplete, and the accusation is getting louder. If the pattern strengthens with more data, it will force physicists to add something new to the theory. If it fades, it will teach a lesson about the limits of precision measurement. Either way, the four-lepton channel has stopped being a confirmation tool and become a discovery frontier. What this changes is simple. The next breakthrough in particle physics may not come from a dramatic new particle appearing at high mass. It may come from a known channel that refuses to behave. It may arrive as a 2% discrepancy that grows into a 5% discrepancy, and then into a 10% discrepancy until the math breaks and the theory has to expand. The Higgs is no longer just a discovery. It is a probe. And the cleanest way to use that probe is to watch how it decays into four leptons. If those leptons keep drawing the same pattern on the screen, the pattern will eventually become undeniable. The question is whether physicists will recognize it before the evidence becomes overwhelming, or whether they will keep calling it a glitch until the glitch rewrites the textbook. If you want to follow how precision becomes discovery, this is the channel to watch.